Hey guys, this is Mr. Mahmood and you're watching the Honors Biochemistry Video 1. Now this is a specific video for the Honors level students because at the Honors level we typically expect the students to understand some of the actual chemistry behind the way that the major organic compounds are structured. Now basically, obviously we can't cover all of chemistry while we are covering all of biology. That's 2 full years of science. But what this video is pretty much going to do is give biology students just enough chemistry background to pretty much be able to walk their way through at least this biochemistry unit, if not the majority of the things we talk about throughout the school year. So kind of your crash course just on basic chemistry and basic bonding in order to make sure you understand what's going on with the structure of organic compounds. In this video we're going to be talking about some of the basic elements that are used in the major organic compounds, specifically the big 3, carbon, hydrogen, and oxygen, talking about why those are important and why they make the bonds that they do. The specific types of functional groups that we'll be referring to that work with carbon, hydrogen, and oxygen, as well as a few other elements that you find often in different categories of organic compounds, and finally talk about the 3 basic categories of bonding that occur: covalent, ionic, and hydrogen bonds. Now ionic bonds aren't going to be as big a deal here in biology. You'll learn more about those and focus more on those in chemistry, but covalent bonds are very important for organic compounds, and hydrogen bonding plays an important role in some of the key biomolecules and how they're held together, specifically when we start talking about nucleic acids like your DNA. So if you're an honors student, sit back, focus, pay attention, because this is really going to come in handy for the remainder of this unit. If you're an on-level student and you're just doing this because you want to take on the challenge, good for you. I like the way you think. Just try to take it all in and really let this build on your overall understanding of organic compounds. Alright, so to get started, we're going to focus in on the basic periodic table. Now, there are multiple elements in the periodic table. In the biology form, we're really only going to worry about 5, really 6. There's sulfur that can show up occasionally when we talk about different categories of amino acids, but really there are 5 major elements that we're going to really hit hard and cover multiple times over the course of this school year. The first one is carbon, the second is hydrogen, and the third is oxygen. Those 3 play major roles in all organic compounds. For a couple of them, we're also going to introduce nitrogen, and then for one in particular, we're also going to introduce phosphorus. So these are the 5 basic elements that we're going to focus in on. To get started, let's focus in on the key element that most biologists would agree is the major functional unit within all living things here on Earth that focus in with biology, and that is carbon. So to talk a little bit about carbon, let's think about what the numbers above and below of the basic symbol would mean on the periodic table, and then this Bohr model that you see here, which is basically a physical representation of its structure. Okay, so carbon has what's considered an atomic number of 6. Now, the atomic number is the number that you see above the letter symbol on the periodic table. That atomic number, by definition, represents the number of protons that are in that atom. Right? So if you see carbon here has an atomic number of 6, then we identify that the carbon atom typically has 6 protons. Okay? Alright, so the atomic number tells you the number of protons. The mass number underneath, for the sake of discussion, it's a little more detailed than this, but let's just go with the idea that the mass number represents the number of protons plus the number of neutrons in any given atom. And normally, when we're talking about a stable atom that's not considered an ion or anything like that, it actually has equal numbers of protons and neutrons. So it's pretty common to see that the atomic mass, the bottom number, is actually double of your atomic number. So here we have an atomic mass of 12. So carbon in particular has 6 protons and 6 neutrons. Now, neutrons are neutral. They're known for that. They have no charge. Right? Protons have a positive charge, and those are both the protons and the neutrons, what you find within the nucleus of that atom, or the center of that atom. So in the center of a carbon atom, you have protons and neutrons, 6 of each, and in order for the carbon to be stable, a typical carbon element, the element itself shouldn't have a charge. So if you have 6 protons, which are positively charged, you should also have equal number of electrons, which are negatively charged. So based on the atomic number of carbon, we can identify that it has 6 protons, 6 neutrons, and 6 electrons. And the electrons are what we're really going to focus in on here, because the focus of our discussion, for the sake of biochemistry and focusing in on biology, is understanding why and how many bonds need to be created with carbon to other elements. So we're going to focus in on the elements here in the representation of what's considered a Bohr model. Now a Bohr model again is an oversimplification. The reality is electrons don't fit this perfect mold of being in perfect orbits around a nucleus or anything like that. They're really pretty scattered, but at any given time proportionally you have a good chance of seeing electrons identified in about this separation. The first orbital, or the first ring surrounding any nucleus of an atom, can carry up to 2 electrons. Basically because of the charges that they have and being so close to the nucleus, you can only have up to about 2 electrons in that first orbital possible. And then every other orbital from that space on, every other ring that extends out, can carry up to 8. So the basic idea here that we're going to start talking about with any of these atoms, when we're thinking about how many bonds it needs to make, is that all of these atoms want to be stable. In order for an atom to be stable, they need to have their outer shell, or their outer subshell, their outer ring of electrons filled. So if that outer shell is filled, then that element is considered stable. And if you have a molecule that has multiple elements, and every one of those elements have that outer shell filled, then that molecule is considered a stable molecule. And in biology, you definitely want stability. Stable is a good thing. So when we start talking about all these elements, think about always wanting that outer shell to be stable. So in this case, carbon has an atomic number of 6, so that means inversely it has 6 electrons. Because what we said in that first ring can only carry up to 2, we can take 2 of those 6 and put them in the first ring. So that means the outer shell in this case for carbon only has 4 electrons. Okay? So we call these outer shell electrons valence electrons. V-A-L-E-N-C-E. This is a very important term that you guys need to make sure you remember. So valence electrons are the outer shell of electrons, and again you always want that outer shell to be full. So in this case carbon has 4 valence electrons, which means it has basically 2 options. It can lose 4 of its electrons, because if you lose that outer shell and it disappears, then the outer shell becomes the one that was just before it. So that's one option, to get rid of 4 electrons, or it can add 4 electrons. And for a few reasons that you'll understand a little better in chemistry, we don't need to get into now, what carbon will actually do is gain 4 electrons and try to get that outer shell filled so that it can be stable. Okay? Now, it wants to add 4 electrons to its outer shell in order to become stable. Alright, so that gets you through carbon. We talk about some of the basic components of it. So with that understood, let's go on to the next key element here, which is hydrogen. Hydrogen, if you look at the atomic number and its position on the periodic table, is the first element, which means it only has an atomic number of 1 proton, 1 neutron, and 1 electron. So it only has 1 outer shell. There aren't multiple shells, right? Because there's only 1 electron. So it's only filling in that first one, and that first shell is not even full, right? Because remember, the first shell can carry up to 2. So that first shell for hydrogen only has 1 electron. So in this case, we consider that to be 1 valence electron. And in this case, since it needs 2, hydrogen will need to add 1 more valence electron. It wants to try to gain one more electron in order to fill its outer shell and become stable as well. Hydrogen in this form is highly unstable, just as carbon is in its form when it just has 4 valence electrons. We need these things to become filled, right? So this will kind of help us understand why the molecules bond together the way they do. Right? Alright, and then the third key element that we're going to relate into here is oxygen. Oxygen has an atomic number of 8, which means it has 8 protons, 8 neutrons, and 8 electrons. Alright, so the 8 electrons come into play when we think about valence shell. So a common mistake, if I ask you how many valence electrons oxygen has, if you just look at the total electrons and say 8, that's not correct. Because even though you think 8 is the ideal number, you want there to be 8 electrons on the outside of that outer shell so it can be stable, you remember that first shell carries 2. So the first shell will have 2 of the electrons, which means the remainder are what make up your valence shell for oxygen. So oxygen actually only has the remaining 6 electrons in its valence shell, which means it's 2 away from becoming stable. That's pretty close. So oxygen is going to work very hard to try to get 2 more electrons added to its valence shell in order for it to become stable as well. Alright, so just remember the basics of the 3 elements and how many electrons they all are looking to gain. So carbon's looking to gain 4 electrons to become stable, hydrogen's looking to gain 1, and oxygen is looking to gain 2. Now the fact that they're all trying to gain something should quickly raise a few red flags that there's going to be a problem here, because everyone's trying to gain something, no one's wanting to give anything away. So we're not going to be able to have this sort of a barter system where we're trading one thing for another and everybody's happy. All of the elements involved are looking to add. So instead of the system that you may be accustomed to thinking of, just one for the other, the kind of relationship and the way they're going to have to work together is going to have to be a little bit unique. All right, so the unique type of relationship that is going to have to happen with multiple elements that are all trying to gain electrons is the idea of sharing these electrons. So this is what we call covalent bonding. When multiple elements are looking to try to add electrons, none of them are looking to give them away. The only thing we can really try to do, and these atoms can really try to do, is get close enough together so that one electron can actually be assumed to be part of two separate rings in their valence shell. So with carbon, for example, you know carbon has 4 valence electrons. It's looking to form 4 more electrons into its valence shell in order to become stable. And each hydrogen, remember, is looking to make one bond as well. So if carbon were to add 4 separate hydrogens and all covalently bond to each other, then every single one of those electrons on the outer shell will be assumed to belong to either carbon or hydrogen and fill that outer shell. So each hydrogen will look to share 1 electron with carbon, and that 1 electron that it's sharing with carbon would make hydrogen stable. And then if carbon shares 1 electron with each of the 4 hydrogens, then it'll become stable as well. So what we end up with is a chemical compound here. This is what we consider methane. This is a gas, and it's also known as CH4. So that when we refer to it here, we can consider it CH4 because it has 1 carbon with 4 hydrogens surrounding it. And we need 4 hydrogens because each hydrogen can only commit to 1 electron being shared. And each shared electron is usually what we consider a bond in this covalent bond. So a lot of times it's also in freehand. You just write it with a line in between the elements. So the same structure you see here on the left can be written in this form. So there are 4 single bonds that are holding together this molecule, and everything involved is now stable. Each hydrogen had 1 electron by itself. It's sharing one of the carbons to fill its outer shell. So each of these hydrogens on the outside becomes stable, and the carbon in the middle, remember, needs to make 4 add 4 electrons, so it's going to make 4 covalent bonds, 1 with each of the hydrogens, to give it 4 more, or at least have it assumed to have 4 more electrons in its valence shell, which would fill that carbon as well. So every carbon likes to have 4 bonds surrounding it. Every hydrogen likes to connect and have at least 1. This is a big component when we talk about organic compounds because the majority of organic compounds and organic molecules we're going to be talking about work around what we consider a hydrocarbon backbone, which means it's nothing but a series of carbons and hydrogens connected to each other with other elements and other functional groups attached to it. So when I talk about a hydrocarbon backbone, I'm basically referring to many of these carbons and hydrogens bonded together. Now, it's not always a carbon having to be bonded to 4 hydrogens. In fact, oftentimes carbon bonds with other carbons. So you'll see a chain of carbons, something say like this. And keep in mind, every time I draw a line, I'm representing 1 shared electron or 1 covalent bond. So this carbon on the far left, for example, has already represented 1 bond, in which case it needs 3 more to become stable. So I introduce 3 more hydrogens. Each of the hydrogens only needs to have 1 bond in order to become stable. So this carbon right here is now stable. But now the carbons that are in the middle of the line, remember, they each have a bond before and after. So 2 of the 4 bonds have already been taken care of with other carbons, which means each of these only needs 2 more bonds to fill. So each one will add just 2 hydrogens. Same here. We'll add just 2 hydrogens in order to fill the bond. All the way down the line, your hydrocarbon chain, the carbons in the middle are taking care of each other with 2 of the bonds, and so you just have hydrogens on the outside. And then this final carbon has 1 bond taken care of with the previous carbon in the line, so then it actually needs 3, just like the beginning line, in order to become filled. So this is what we call a hydrocarbon chain. This is the basic component of all organic compounds, and this is something that we're going to build on with all organic compounds along the way. Now, not all of these hydrocarbon chains are as straightforward as you see here. There are a lot of variations, a lot of functionalities that make it very unique. For example, not all of the bonds happen to be single bonds, because remember, each bond represents 1 shared electron. Sometimes you may have a situation where between 2 carbon atoms, you're not just sharing 1 electron, but possibly sharing 2. So if 2 of the 4 electrons are being shared here, now we have what's considered a double bond. So 2 of the bonds are already taken care of just between those 2 elements. So now each of these carbons has 2 bonds taken care of between the carbons that are double bonded, 1 carbon with the one before or after the chain, which means they only needed 1 more hydrogen to fill. So that means that each of these carbons are now stable as they are as you see them. They didn't need those hydrogens coming down from the bottom because that would actually add an extra electron, make a whole new valence shell, which would now make their valence number go from the perfect 8 to 1, which makes them extremely erratic and extremely volatile. So this is a stable molecule because that double bond actually takes care of it. In reality, that double bond will also cause a bit of a bend, which will get this whole structure to actually angle a little bit, which plays a very important role when we get into lipids especially. So just remember the basic components of hydrocarbon chains, and basically how every carbon is looking to make 4 covalent bonds, every hydrogen is looking to make 1. Okay? So these covalently bonded molecules are very strong because if you think of this as sort of like an atomic tug of war, both elements are looking to assume an electron being put into its own valence shell, which means neither one of them is looking to let go of any electrons. They're both grabbing onto an electron and assuming it to be part of themselves, so they're both pulling very hard. So it's literally like a tug of war. So that kind of a pull from both directions causes a very strong bond. So covalent bonds are the strongest of these bonds that we're going to be referring to, which is great for organic compounds because, again, if things fall apart, you lose stability. So stability is very important. You want your molecules to have these strong covalent bonds. Now, there are downsides to this. If I were to want to break a covalent bond for a number of reasons, it does require more energy. But that's the price your body takes to make sure that you have the stability of your organic compounds. So covalent bonds are very strong because they share these electrons like you see here. All right, so functional groups then are representations of other types of bond combinations that you'll see in a lot of the major organic compound categories. And every one of these functional groups are covalently bonded not only within themselves but to the hydrocarbon chain or to the rest of the organic compound or the molecule that it's extending out from. So there are a few basic categories, examples of functional groups that you should probably know as we go through this biochemistry unit, and they deal with the elements that you see in front of you. So again, we've already talked about carbon and hydrogen and oxygen, the first, second, and the fourth. Carbon needs 4 valence electrons, so I'm just going to put a +4 here to remind you how many bonds, covalent bonds, it needs to make in order to become stable. Hydrogen needs 1 to become stable, just because it only needs to worry about that first subshell, remember, and it can only have up to 2. Oxygen, we've already talked about, has 6 valence electrons, so it only needs 2 more to become full. As for the other two, here are some new ones. Here, this N is nitrogen. Nitrogen is going to play a very important role when you get into your amino acids and your proteins and your nucleic acids with the nitrogen bases of those nucleic acids. Now, looking at nitrogen, its atomic number is 7. Again, 2 of those electrons are in the first shell, so that means it has 5 valence electrons. So if it has 5 valence electrons, it's looking to become filled. All it needs now is 3 more bonds. So nitrogen is going to need 3 bonds in order to become filled. And now you're left with phosphorus. Phosphorus is a unique animal. It has 15 electrons. So in sense, it seems like it works much like nitrogen. It has an extra shell, but it has 5 valence electrons. So you would think 3 electrons would stabilize everything and everything would be happy. But for multiple reasons that would take a lot of time to discuss now, you're just going to have to go with me on this. Basically, instead of what's considered the s and p orbitals, phosphorus now has the d orbital to work with, which means the bonding works a little bit differently. But phosphorus either likes to have 3 bonds or 5. And in the case of the organic compounds that we're going to refer to, we're going to think about this 5 bond necessity for phosphorus. So again, just trust me on this one. You'll learn more and understand why later. But phosphorus works a little bit differently and actually requires, in this case, 5 covalent bonds in order to become stable. So let's talk about some of the different organic examples of functional groups. All right, the first functional group we're going to talk about is called a hydroxyl group. And a hydroxyl group, it's a type of alcohol, and alcohols typically have an extension of these 2 elements, oxygen and hydrogen. Now again, we have a hydrocarbon chain. All my functional groups are going to be connected to a hydrocarbon chain. So that first bond is to the end of that carbon. So there's already 1 bond happening there, and here's where the oxygen is going to attach. So you have an oxygen already attached to a carbon, which means, again, because oxygen needs 2 to fill, it needs 1 more covalent bond. And if you introduce 1 hydrogen to that, everything becomes stabilized. The oxygen has the 2 it needs, hydrogen's happy as well, and now we have a stable molecule. So if you ever see this extension, in shorthand we just describe it as an OH like this. This is what we consider a hydroxyl group. Okay? Besides a hydroxyl, we also have something called a carboxyl. Carboxyl is going to be similar in formation. You are going to have an actual hydroxyl group in a carboxyl, but it's a little more detailed. So you have an extension from a hydrocarbon chain. You have a carbon that actually has a connection to oxygen as well as a hydroxyl. So if you think about the mathematical combinations, this doesn't look like it makes sense. Remember, carbon needs to have 3 bonds. If it bonds to 1 here, the oxygen, remember, only needed 1 because it has the hydrogen on the other side, so oxygen stable. If we just had a single bond here to this other oxygen, there'd be 2 problems. One, this carbon has 1 less electron than it needs, and so does this oxygen, because remember, this oxygen needs 2. But if we allow this bond to actually be a double bond between the C and the O, everything stabilizes. So this is the actual formation of a carboxyl group. It's a C with a double bonded O and then a hydroxyl group attached to it. So you'll see carboxyl groups quite a bit as well. Another example is a carbonyl. Carbonyl group is much like a carboxyl group, except with a carbonyl group you just don't have the hydroxyl. So you have an extension from a hydrocarbon chain, a carbon with a double bonded oxygen, but instead of an OH you just simply have 1 more hydrogen to make everybody happy. So this is a carbonyl compared to a carboxyl. Carboxyl actually has the hydroxyl within it, right? Another example of a basic group is what we consider an amine group. An amine group, anytime you hear amine or amino, it's usually referring to nitrogen. So when you talk about amino acids, you're hopefully going to remember that they have an amine group in them and they have nitrogen components within them as well. In this case, remember, it's connected to a hydrocarbon backbone just like the others. We have a nitrogen, and it needs to fill just with hydrogen. So remember, nitrogen needs to make 3 covalent bonds in order to fill. One of them is already with a carboxyl group, so 2 more bonds are needed to be made. So you just add 2 more hydrogens and everybody's happy. So an amine group is something you're going to see with amino acids and with organic compounds like your nucleic acids, like your DNA. The final group are phosphates. Now I'm probably going to run out of room here to describe this, but a phosphate is the one that's kind of the extension of the rule. This one is a phosphorus that's actually going to require 5 oxygens. And again, we're going to mess things up because not everything's going to be stable. So you're just going to, again, have to trust me on this. But a phosphorus, actually a phosphate group, will have a double bonded O, so this seems good so far. That oxygen's full. But then a lot of these other oxygens that it's going to bond with, 4 of them in exact, are not going to be double bonded, which means each of these are going to be charged in a way that's going to require them to look for bonds. And that's actually a good thing because most phosphate groups serve the function of giving the attractive force necessary for a lot of your organic compounds to work the way that they should. So this is what we consider a phosphate group. Now I don't really expect you to memorize any of these, and I doubt that any of your teachers otherwise would expect you to memorize these. However, they do make the structure of organic compounds make a lot more sense when you understand why they're made the way they do. And again, with the exception of phosphate, again, you're just going to have to trust me on a couple of things so we don't sit here and use up another 30 minutes just talking about it. The other organic compound functional groups, you can see why they have the bonds that they do. All of these are in order to stabilize that outer shell, get that valence shell full so that everything can be the equal number that you're looking for, that full outer shell. Okay? Now that's all for covalent bonds. And in covalent bonding, again, the whole goal is the fact that everyone's looking to gain, so the only thing they can do is share those electrons. And since they're both holding onto those electrons very firmly, that bond is very, very strong. So of these 3, covalent bonds are the strongest. Now this next category of bonds, ionic bonds, are the weakest of the 3, because this is much more like the barter system that you might be thinking of from the beginning. One is looking to get rid of an electron, the other one's actually looking to gain. And a good example is anything from the sodium group and then the whole fluoride group, which includes chlorine and other elements as well. So NaF is a common salt that's found in your toothpaste. Anytime you talk about fluoride in your toothpaste, it's usually sodium fluoride like this. And then NaCl is common table salt. So there are a lot of basic compounds that you use every day that are ionically bonded together like this, and they come from these basic columns of the periodic table. And the reason these columns work together so well is because every column has about the same number of valence electrons with a few various exceptions. So the sodium column, in this case, we'll look at sodium as the example, it has 11 valence electrons. So that means 2 of the electrons are in the first subshell, 8 in the second, that makes 10. So that means there's 1 electron left over. So this sodium is just desperately looking to get rid of that electron. If it can get rid of that 11th electron, that whole outer shell disappears, and now its valence shell is the full shell that was underneath it, which is exactly what sodium wants. So all sodium is looking to do is get rid of an electron. Now that's a new scenario here because everything we've been talking about up to this point are elements that are looking to gain. Now sodium is actually looking to get rid of one. And on the other side, if you look at something like fluorine or chlorine, they both have the same number of valence electrons, even though they have a different number of rings. In this case, fluorine has 9, atomic number of 9, so 9 electrons. 2 in the first subshell, so that means 7 are in the second. It's desperately looking for just 1 more electron to fill. So if you have something like sodium that's looking to get rid of an electron, something like fluorine that's looking to take it, these are a match made in heaven. They're both very happy to either gain or receive an electron. So in this case, because the electrons are actually moving in one direction and will eventually be passed over to something else, this type of bond is more temporary and is pretty weak and fairly easy to separate. Once the fluorine actually accepts the electron from sodium, then the fluorine now has one extra electron than normal, which means it has a negative charge, whereas the sodium, now because it gave up that electron, has one less electron, which gives it a positive charge. So this is where we get charged ions. The whole idea of ions and components that can deal with conductivity of electricity and everything else that we'll be dealing with when you move on to chemistry, it all comes from these ionic bonds, where electrons are actually passed from one element to the next. Now, once this thing is passed off, they're both pretty happy with their new composition of electrons, which means they can pretty easily be separated. There's no desperation of sodium trying to hang on to that electron that it dropped off for any reason. Once it's passed it off, they're both filled, they're both happy, they're both stable. Even though they're now charged, the fluorine is negatively charged because it has an extra, the sodium is positively charged because it gave one away, they will very happily separate. So ionic bonds are actually very weak, which is horrible for organic compounds. You definitely want your organic compounds to have that strength and stability and not break apart very easily. When we talk about our organic compounds and biomolecules, we won't be referring to ionic bonds at all. So everything is going to either be covalently bonded, or, as we're going to talk about here, hydrogen bonds will play a very important role in a few of the organic compounds. Hydrogen bonding is actually not a bond at all. In fact, it's more of an attractive force. So think of like a magnet, how the positive charge of one magnet and the negative charge of another will attract to each other, and that connection is actually fairly strong depending on the strength of the magnet. It's hard to pull them apart. That's what I'm thinking about when I'm talking about hydrogen bonds, the strength of that magnetic attraction between two opposite charges. The basic component, and truly understand hydrogen bonding, the best example is to look at a water molecule. So water molecules, as you see here, are nothing but two hydrogens connected to an oxygen, right? So looking at this molecule here of water, kind of looks like Mickey Mouse basically, right? The ears are the hydrogen and the face of the Mickey Mouse is the oxygen. So if you look at the basic structure of this water molecule here on the right, of the whole molecule, say we'll start from top to bottom, from here to here, the majority of the electrons are all in this area and down, right? So this area covers most of the electrons, the negatively charged electrons, and the majority of the protons, remember, are all in the nuclei. They're all in this range and up. So from here up are most of your positively charged protons. So if you think of this whole molecule, even though the whole molecule is stable, the majority of the positively charged components are here towards the top. So this top area, and particularly these hydrogens, are usually considered to have a slightly positive charge. So we use a delta here, and I'm going to try to draw a delta. I think it's something like this. Delta charge means partial charge. So even though the whole molecule is equal, the hydrogen side of this is actually partially positive. And because there are more electrons towards this lower end is actually partially negative. So within the whole molecule, you'll have a slightly negative charge on one side where you have more electrons, and you have a slightly positive charge on the other where you have more protons. So because of this natural magnet that's developed basically between a water molecule, if you have multiple water molecules in a solution like you see here on the left, the negatively charged oxygen sides will attract to the positively charged hydrogen sides. And these water molecules will attract to each other all with the same basic components. These will naturally attract to each other because the positively charged hydrogen, or not, the partial positively charged hydrogen will be attracted to the partial negative of the oxygen. So these water molecules naturally collide and attract to each other, and that's a very important component in how water works in a lot of different systems. We're going to talk about them with weather patterns. We can talk about them with the cohesive property of water, is what makes water stick together and what gives you the surface tension on the surface of water, its ability to adhere to surfaces and to attach to them. It's what makes graduated cylinders have this little concaved meniscus, or this curve in itself, because it attaches itself to the side because of the hydrogen ions and the hydrogen bonds ability to attach to the sides, as well as the surface tension from the cohesion of the water molecules being pressed down because of gravity causes that curve. So there are many components of water that have to do with these hydrogen bonds. So hydrogen bonding is really nothing more than an attractive force between a slightly partial positive end on one side, usually of that hydrogen, and a partial negative charge of something else. The attraction of those two causes something that we consider a bond. Even though there's no actual chemical bond occurring, there's no sharing of electrons or passing of electrons, but there is enough of an attractive force that we consider that to be a type of bond. Hydrogen bonds play a critical role, especially when we get into your structure of DNA, which is a major organic compound as well. So hydrogen bonds, even though they're not a bond, they are actually stronger than ionic bonds. So if we were to put these in order, the strongest of the three is definitely your covalent bonds, because they're both looking to share electrons. Then we have hydrogen bonds, which really isn't a bond at all, more of an attractive force between partial positive and partial negative charges. And then the weakest of the three would be ionic bonds, because they are perfectly happy after the exchange has been made. One is looking to gain an electron, the other is looking to lose, and so they'll separate out fairly easily after they've passed on their electrons, even though they now became charged, either positively charged if they lost the electron, or negatively charged if they gain it. So this is pretty much it. That's your crash course of chemistry. Hopefully you took it all in, and I guarantee you will have a much deeper understanding of organic compounds and biochemistry after you have a basic understanding of why the structure of these things look the way they do, why the bonds are formed the way they are, why they're as strong as your teacher tells you they are. So hopefully this was helpful for you. Again, this was an honors level video. It will come in handy if you really make sure you understand this. Alright guys, thanks a lot. Take care, and I'll see you next time.